Thanks, everybody, for the opportunity to come talk to you about SETI. And we traditionally think of SETI at radio wavelengths. I'm going to now push us into the SETI realm of optical and infrared, and in particular, looking at the interest of looking for laser communication between extraterrestrial intelligence. I'm going to talk about two projects today. One is an existing one that we're doing at Lick Observatory right now, doing the first near-infrared SETI search. The second is a conceptual design that we're quite excited about for an all-sky, all-time optical and wide-field optical and near-infrared system. There's lots of people to this project. The stars indicate the undergraduates and graduate students that have worked on this project, and we've really tried to incorporate students throughout this program. Okay, lasers, invented in 1959 by Charles Towns. Immediately after he invented it, he realized the magnitude and the use of using lasers for interplanetary and interstellar communication. In 1983, he published a paper where he tried to investigate what wavelengths we really would like to search at for SETI. I included one of his quotes. The above discussion indicates that the infrared is as good as, and maybe more favorable region for SETI than the microwave region on the basis of reasonable assumptions. This may affect the scale and style with which SETI is carried out on Earth, even in the immediate future. Well, that was in 1983, and it took us several decades later to actually start embarking on this in a very large survey sense. All right, so we're looking at lasers. They can be continuous, they can be pulsed. We can do this search in a variety of methods. One is, for instance, using the automatic planet finder, where we use a spectroscopic search to look for a continuous or maybe a very rapid pulsed laser. There's advantages for this. You can get to very low sensitivities if you lose large apertures like the Keck telescope. But the continuous laser, if you were to do this communication and you had a long time pen pal between interstellar stars, would require a lot of power. Okay? You also need high resolution spectra for scanning for that narrow emission line for which the frequency we don't know. Okay? And there's been a couple searches for this done by Keck. Nate Tellis just posted a great paper where he shows the power and sensitivity of using the Keck with the high-res spectrograph. But the difficulty with this, with most SETI searches as well, is that they're pencil beam surveys. We're looking at one star here, one star there, one star over there, and you can get to about 5,000 to 10,000 stars doing this search method. Alternatively, you could do fast time searches. Okay? So to weed out that stellar background, you eventually go to very fast time domain, nanosecond level, so you're looking for a burst, right, a pulsed burst, where that would be unique if you had photons arriving and stackpiled in a nanosecond time. This is easier to search. Instead of looking at a particular frequency across the optical bandpass, you don't care. You're just looking for that big pulse across all of that background optical or infrared light. It also requires less power. Okay, so if you want to be energy efficient as a transmitter, there's a plus there. But you allow, with these very short timescales, to get below the swamped backgrounds, which we'll talk about here in a second. And lastly, doing pulse searches is you can do targeted searches, as I'll first describe, and it has the flexibility of essentially putting this to wide field of areas in the sky. Okay, why is infrared a prime region for interstellar communication? One, you just get reduced stellar background. Okay, you're falling across the curve, especially if you're searching around massive, bright stars. So you just have less stellar background at infrared wavelengths. You also have reduced galactic background. So NGC 0628 is kind of an analog to the Milky Way galaxy. This is its spectral energy distribution all the way out to 30 microns. You see all the PAH features here on the right. Here it is on the near infrared. Of course, this is just, everybody was the pesky M dwarfs, right, if you're an extragalactic astronomer, on the tail end of this curve. But besides the stellar and galactic background, which is reduced at the infrared, another prime reason has to do with extinction. So if you look at extinction through the galactic plane, and let's say you were going to transmit a signal using an optical laser here at about 0.5 microns, okay, at 0.3 kiloparsecs, you lose your emission by 60%, or 40%, I should say. You only get 60% transmission. But in the near infrared, you get boost. You keep up, and especially if you go out to the further infrared, you don't get interfered by interstellar extension. So if you care about the number of photons arriving on the other side, then you would push yourself to transmit at infrared wavelengths. And the problem only gets worse if your pen pal's further away. Okay, so why near infrared now? We've done optical SETI for several decades, and that's mainly because the detectors were available to us at that time. We needed fast response detectors. The one that Jill referred to at the beginning, we used fast photomultiplier tubes. But to get to photomultiplier tubes into near infrared or infrared wavelengths, you don't have the necessary quantum efficiency to do that. What became available in the last several years is in-gas avalanche photodiodes that use a very special readout called discrete amplification. And for time reasons today, I'm not going to describe that readout process, but it in fact is very important to a part of why we selected these detectors. But these discrete amplification APDs are great. You get these half nanosecond level pulses, and you're able to discriminate against large dark pulses as well as a background of a sky. So we purchased some of these, tested them in the lab, realized that they would work for SETI, and we built an instrument and commissioned it. So in March 2015, we had first light on the nickel 1-meter telescope right up here at Lick Observatory. We can see it, especially if you're driving down the 101. It's a compact, small instrument. It's meant to be built cheap. We wanted to do off-the-shelf components and make this easily transferable to potentially other systems. So the light, this is sitting at Cassegrain at the 1-meter telescope. The light is coming from down here, up here. There's a hole. It enters a dichroic. It splits the light here into the optical. There's a guide camera. Our detectors are tiny, so we need to do alignment and pointing. The infrared light gets sent through here. We have a filter wheel, a beam splitter, which lends 50% of the detector 1 and 50% of the light to detector 2. We like two detectors, right? Because if we do get photon pileup, we want them to pile up on both detectors at the same time. This allows us to confirm our detection and allows us to weed out false positives. I will say also that we have a laser unit here that's infrared, and we can push this in and out, and this actually helps us with our alignment, but it's nice for proof of concept, as I'll show you. So we do real-time processing in the system. One of the things that we made sure to do in this new system was to try to save and record as much of the waveform as we possibly could for post-processing as well. Here's an example for a waveform of detector 1 and detector 2. Here's a simultaneous pulse. Here's a spurious pulse. And what you see here in purple is a threshold that we're setting to discriminate against the lower ambient noise. So we can do coincidences between the two here, and we can look at the pulse height distribution, the number of pulses and the height of them, histogram, and compare that to coincidence models and the likelihood and the probability of a detection. We also can take the Fourier transform it and look at the periodogram, and we have real-time alarm and notification systems. Here in this case, we had 2 alarms. I think we were looking at our laser in this case, but it gives you an idea that our notification system is working. And at the end of the night of all our observations, these reports get sent to the entire team. So this is what, I thought it'd be nice to show what a booming signal would look like in a system if we actually did get a signal. So this is pushing in that stage. We have our laser. We're pulsing our laser here. We have red here is detector 2, right? Blue is detector 1. You see them nicely arriving at the same time. Here's our pulse height distributions. We have, here is detector 1 and detector 2 of the pulse height distribution. Here's the coincidence measured. And here's the deviations, right? This is of interest from the pink curve, if you just had your dark of your detector versus the coincidence model here. Okay? So you can use this real-time pulse height distribution, even on a single detector, but it's nice to have more than one detector to do that confirmation. Okay, what are we looking at? We purposely matched our target list to the breakthrough listen target list that Andrew Siemion mentioned, that Howard Isaacson has his paper out in 2017 about. This was, of course, limited to whatever we could observe here at our latitude at Lick Observatory. We're looking at giants. We're predominantly looking at main sequence stars. We've looked at some Earth's transit zones. We have 27 of the nearby stars in our target list. For these systems, we do monitor more than once. We have galaxies that we do, usually at the core, we do drift scans across them, globular clusters, exoplanet habitable zones, and then other astrophysical sources and fun sources that we like to throw into the mix. Of these, now our campaign after 2 years is 79% complete. We've looked at about 1,060 sources. Of that, about 1,379 observations. We're running about 10 to 12 nights per month. All of those observations are done at UC San Diego remotely by undergraduates. So it's a great opportunity to get students involved. So far, of 1,379 observations, we've had 3 alarms. Okay, so all of those sources have been continued to be monitored. If you look at the probability of those alarms, this is the probability of coincidence occurrence versus the average coincidence rates during each acquisition. Everything you see here are observed 1,379 sources here. In red here matches what our false alarm rate we decided to select for our survey. Because if you try to lower your false alarm rate, you decrease your sensitivity. So we took the trade-off for that. And indeed, if you look at our 3 sources, they fall roughly here. And the alarms with respect to all the acquisitions show that there was a 20% probability of them. So we expected these guys. This is being written up by Jerome Mayer, who's a project scientist at UC San Diego, and he'll do a survey present the survey results for the entire program. So this is where we're at today with a near-infrared SETI. I want to move us into what we can do next. Again, this is a pencil beam survey. We would like to expand this to wide field areas of the sky, or better yet, the entire observable sky. We can do this. So the detectors we worked at in near-infrared are now being put in arrays. So this is an example. This is a 5x5 array that we put. Again, this is operate from 900 to 1,700 nanometers. Hamamatsu started making these same type of detectors. They changed the name, but it's essentially the same readout process. They're called multi-pixel photon counting devices. These things we can also array and tile to try to cover large areas of the sky. So using these detectors, we started investigating ways to do our collecting apertures. And one of the best ways to do this is using Fresnel lenses. Okay, they're efficient, they're lightweight, they have fast focal lengths, f1 focal lengths. They're transmissive all the way from optical into the infrared, and they're extremely cheap. Before, when we started designing this, we went back where our old astronomer hat, started thinking about mirrors and glasses and regular telescopes, and those would roughly cost us about, on the cheap side, if it was spherical, about $10,000, but most OTAs that we needed would be about $100,000. Ouch. If you need an array of a bunch of $100,000 telescopes, that would cost a lot of money. Fresnel lenses cost us about $100 or less. So we investigated them, and we investigated whether they would have the wavefront error and the spot sizes we need to match our detector size, which are about 3 millimeters in size. We bought a 0.5 meter Fresnel lens, we tested it in the lab, and indeed, even 5 degrees off axis along this Fresnel lens, you get a spot size of about 2 millimeters in size, which is well matched to our pixel size scale. Now, what do you do with these Fresnel lenses? Well, they're cheap. They're $100. You can behind each one, you can tile them with detector and detector arrays. Imagine then you can tile them across the observable sky. A nice way to do this is using geodesic domes. They're structurally stable, and you can actually modularly plop in each one of these Fresnel lenses with an outer dome of Fresnel lenses and an inner dome of detector arrays. So here's an example I'm showing you on the right of one of our CAD drawings. It's about 126 Fresnel lenses, each a 0.5 meter in size. And with this, you can cover instantaneously 10,000 square degrees. Now, we want confirmation here if we're going to make this big discovery. So what you really would like are two of them. So if you imagine if you have one of these here at your location here in California, okay, you're covering the northern hemisphere. Over the year, you're doing that entire northern hemisphere scan. You have a secondary site as well that's also doing the same simultaneous measurements that can allow for confirmation for signal. We can also put in near-infrared SETI. Now, near-infrared detectors, just like in every other astronomical mission, are more expensive than optical ones. We can't array right now all 126 Fresnel lenses with near-infrared arrays, but we can take a few of those and do the first ever wide field search and drift scanning mode with near-infrared wavelengths. So if this is to scale, okay, you have two lenses here, and you're scanning a 3 arc-minute by 43 arc-minute field of view, and you can scan the observable sky, albeit not instantaneously like the optical, but you can scan that over 3 years with 50% efficiency. That would be the first time ever doing that. So the advantages of this new phase space is that you'd extend and do the first wide field searches to the desirable, what I would argue, and Charles Towns would argue, the desirable near-infrared wavelengths. You could investigate the entire observable sky, increasing field coverage by a factor of 30,000 from Paul Horowitz's wide field optical SETI work he's done previously. And if you look at target pencil beam surveys, by a factor of 3 million. You can increase the fraction of time observed on any given source by a factor of 100,000, because you're just continuously observing it. And you're enlarging the number of observed sources from tens of thousands to hundreds of millions. And my last comment to that, there was, I think Jill pointed out, saying SETI looks for ETI around habitable worlds. We don't care if they're around planets here. We're just looking at the entire sky. Okay, I'll end there. I see I'm short on time.
Okay, Gabor has a question here. Now, there's a mic, yeah, right here.
So I realize that this will be hard to answer, but sort of what's the sensitivity? In other words, what kind of signal would you see?
For the optical detectors, our sensitivity limit, we put it in 25 photons per second per pulse in that nanosecond pulse. That's how we define it usually when we talk about pulse SETI. In our near-infrared, we get about 100, it would take 100 photons per second per pulse. Okay.
What does that translate to in terms of brightness of the?
Well, it depends on how continuous or whether they pulse it, but we can get to megawatt scales of laser emission.
Okay, question way over by the window.
Hi. A number of us are building low Earth orbit to ground optical communication systems. And so we have these ground stations, which are essentially telescopes with ultra-fast receivers and signal processing chains on them. If my spacecraft isn't in view, can I do something useful for science with that ground station?
This one here.
No, mine.
Oh,
my ground station, which is designed to receive gigabit downlinks from LEO satellites.
Yes, maybe.
But when the satellite's not there.
Yes, and I think, not for the purposes you're going to hear about, but I think David Williams will talk about making use of other current facilities, in this case, Trankov radiation detectors for using for SETI searches. So if you have things that are imaging large areas of the sky that have good time resolution and good sensitivity, and you can, have confirmation in signals you get, then yes.
Okay, thanks.
Additional questions?
I think there's
here in the front. Oh, all right. You come next.
What is the equivalent of RFI, especially for the all-sky future surveys? Is there things that you worry about?
Yes. For this, we're worried about, Trankov radiation is one. The other one is, given the parallax of maybe geodesic satellites. We need to think about the altitude of those and what other signals and things that they might be transmitting. But
All right.
in that case also, it might be useful for other reasons.
One last question.
Is there any plan to build one of these in the southern hemisphere where you have a better coverage of the galactic plane, where you'd have more potential sending
Yeah,
sources?
we plopped it down in California because we're sitting here in California. But the idea of this is, yeah, you can put this down in the southern hemisphere, and presumably that's exactly what you would want to do.
Actually, that's what you need to do if you're going to say all sky all the time, right? You need multiple of these.
Yeah, that's fine. I'll put my air quotes of observable sky, but
But that's
like,
really what we want to
yeah,
do, all the time, all sky,
fair enough.
all frequency too. We got to get there. Thank you.
Thanks.